So, okay, in the last week, we were discussing about the convolutional neural networks, where we were discussing about the differences that we can see, that the contrast that we can observe from the feed-forward networks, like fully connected networks, why we are moving to convolutional neural networks for applications like image classification, neural style transfer, and object detection, and so on. And also, we discussed the theory behind it to get some intuition, like how to use a filter to detect features like edges in images. And I said that it's not just an edge, but in different layers of a neural network, depending on the layer, that particular filter may capture some of the features which may differ from the edges. Some in the earlier uh, features may be like horizontal edges, vertical edges, and so on. Later, if it is a face recognizer, then it may be some curves, small curves, upward curves, downward curves, and so on. The third one would be detecting stuff uh, like noses, eyes, mouths and so on. And the next layer would be detecting faces. Those kind of abstraction automatically happens in a deep neural network, right? So in each layer, in the convolutional layer, we can see we are training some weights in the filter. For example, if the filter is a 3 by 3 filter, we can we have to learn 9 weights and 9 biases to train that particular filter. Right? And we were discussing about a single filter, single image kind of scenario for simplicity. But today we will extend that scenario further so that you guys can get in touch with the real world examples with convolutional neural networks. So that is why I try to come up with the convolutional neural network architecture in today's session so that you can understand how the current convolutional neural networks are designed. Right? Actually, these are not the only convolutional neural network architectures. There are many, but these are some of the well-known textbook examples. So there are no textbooks, but these are some samples that are coming from recent papers, well-known papers in the community, right? So, and also, uh, let's start for by explaining some of the historical stuff, how the people have come up with convolutional neural networks, which we haven't done in the last week, right? So convolutional neural networks were designed, as I said, to overcome the problems with fully connected feed-forward neural networks. But this was actually also something that scientists observed in human or animal retina. Retina means the where the images are created in a eye, right? A human or mammal animal's eye, where the images are generated. So that is known as retina, right? So this is in the back of the eye, which has the color of black, right? So which is connected to the optic nerve, is directly connected to the brain, right? So when the retina gets images, so it is connected to the optic nerve, and then it is connected to the brain directly. So in the brain, uh, scientists have tried to understand how the neurons are organized in the uh, brain, right? So then they have found that there are layers of neurons that are they are like shining layers of neurons that were there. So once they were examining how these neurons were working, so they have come up with the initial understanding of the layered architecture of convolutional neural networks. right? So that is how they thought the images that they capture from the retina is processed layer by layer in the mammal brain. So in order to understand the image, so in the nervous system also, we have a layered architecture of neurons so that each layer is processing different levels of features of the image, and these images are processed and their information can be extracted and identified by the brain, right? So actually, in these days, now we have developed similar kind of convolutional neural networks, and we have uh, some explainable capabilities as well. That means, for example, I said that some of the layers are capturing edges, some of the layers are capturing curves, and so on. Right? So how do we know it? Actually, some researchers in some papers they have shown there are the ways to identify what each of the feature is capturing. Actually, we can see what each of the feature is capturing during the training process in the convolutional neural networks. What each of the feature is corresponding to, right? Like whether this one is what is this particular new, what is this particular layers, this particular neuron is triggering at. So what it is corresponding to. So it generally you can see a matrix of edges, matrix of curves, and so on. Like I have drawn in the whiteboard last week. So actually, you can see them uh, when you implement this explainability capability. We are not going through how each of them are done in this lesson, but if you are interested, you can see like maybe you can implement such kind of scenario and identify the nature of your data set, right? So for example, if you have a lot of human eyes or something, that means there are a lot of people with eyes, right? So there are a lot of dogs, that means there are a lot of dog images in the data set, right? So in such a way that not really there are images, but your problem is relevant to identify those particular features. So for example, if it is a cat image classifier, there would be a lot of cat images, cat related features like whiskers, tails, skin color, and all those things, right? So all those things would be uh, embedded into, will be automatically embedded into the features of the neural network, the convolutional neural network. So you can see it what each of the layer and each of the weight is corresponding to, right? So that is the level that we have with the current convolutional neural network. Uh, so in the today's lesson, we are not going into those kind of things, but if you are interested, you can search how they are done, right? So in the last week, we were on discussing about a scenario where there are only one input image or a matrix, and once we apply a filter, then we get a output matrix or a set of features, right? So so this is the exact example that we were using. For example, if you take only the red image, red matrix, which was the same matrix that we used in the last week, and if you use this the front filter, which is W1 to W9 matrix as the filter, then you will get this new matrix, right? Or the output or the target matrix. So you can see like once we apply this filter in each of the location of the image, for example, like this one, for if the stride is one, we go from this location, this location, and so on, right? So, and then you can calculate the values for each of the values in the new matrix. And you can see also the size of the new matrix is much lesser than the original image due to the boundaries, right? So, and also we discussed that how we can avoid it by adding some padding, right? Which is when we are doing it without padding, it is known as a valid convolution. when we are applying padding so that we get the same uh, matrix size as the output. So that is known as same convolution, right? So those are the two convolutions that we use. So depending on the padding we use, that depending on the filter size we use, and the depending on the stride we use. Stride means you can remember, right? Whether you are going from one pixel to the other pixel when we are moving this filter, or if stride is 2, then we can go from this pixel to this pixel directly. That means skipping 2. So that is stride, right? So with stride, filter size, inputs image size, and padding size, all those things, then we can calculate the new matrix dimensions. So we are given the formulas and so on in the last tip. So you can use those information when you are developing a neural network, a convolutional neural network with TensorFlow or some other library, right? So in this lesson, so here you can see now that we have not only a single input matrix, but there are 3 input matrices, right? So one is, so in here you can see there are RGB values, red, green, and blue values. For each of the 3 color 3 channels, we have 3 matrices. And for these 3 matrices, we have to use 3 such filters, similar filters, but with different weights. Initiate with different weights, so they will be trained as different weights. And still then what we get as the output is the same 4x4 a new matrix or the output matrix, right? So what happens is, when you apply this filter, so if you have 3 channels, so this is known as a 3-dimensional convolutional neural network because there are 3 dimensions. First dimension is this one, this one. First dimension is this one. Second dimension is this one. And third dimension is this one, the depth, right? So this has a depth of 3 for 3 channels. And so for 3 channels, we should need a filter with a depth of 3 as well. So once you apply this filter, what happens is, like we said in the last week, so this front filter will be applied to the front 9 pixels, and the second filter will be applied to the second green color matrix, the 9 pixels. And the third part of the filter will be applied to the blue images, 9 pixels. And then we get linear combination of all these 9 by 3, 27 values, and we get the linear combination. That means we multiply W1 by 3, W2 with 0, and so on, and W2 with whatever the green value we have, and so on, right? With the W31 with 7, and so on. And all those things, all those values are added, and then only we get the value for this matrix, right? This is how we do a 3-dimensional convolutional neural network. So this is how we explain it, right? But when we are really applying it, this is what really happens. That means we can have, suppose we have 2 filters, right? For example, for the horizontal edge and the vertical edge. Horizontal edge, this is for the vertical edge. Excuse me. So when you have 2 filters, both of the filters will be applied as mentioned earlier. This filter with these 3 matrices, these 3 filters with these 3, this is actually a single filter. This one is a single filter. These are 2 different filters, right? Each of the filter will be applied with these 3 matrices, or the three-dimensional matrix, or the rank 3 tensor, right? So this is not known as a tensor, right? Because this is not a matrix, because this is a 3-dimensional structure, data structure. This is known as a tensor, right? So as I mentioned some time back, also matrix, a vector is rank 1 tensor, matrix is a rank 2 tensor. This is a rank 3 tensor, right? So when we apply the filter, convolution filter with this image, we can get this green color new matrix, and then when we apply this filter with these images, this image matrices, we get this gray color output uh, matrix. So when we apply multiple filters, we get multiple output matrices as well. Right? So in the earlier case, what we have shown is that when we have multiple channels, when we apply a filter with multiple channels, then we get the same output matrix. But when we have multiple filters, then we would get for both filters, we will get two output matrices. So this output matrices will also be a tensor, which is also three-dimensional. Right? If you have another filter, then there would be three. So there would be three dimension. There would be the depth of three. Right? Now also it is three-dimensional, but there are only two such matrices. When we add more and more filters, there would be more and more. There would be more and more output matrices that would be generated. Right? If we add more and more filters, we can get more and more output matrices. So in the convolutional neural network, adding more and more matrices means we can capture more and more data in this layer, in this phase, right? When we are having more and when we are having more such matrices, that means we have more parameters, right? So suppose that so when we are adding more and more filters, uh, any idea, like any intuition why we should add more filters with basic machine learning theory? Because we have a higher bias, right? That means we realize that, yeah, now we want to reduce our bias. So then what we can do is we can increase the number of filters, which would eventually increase the number of parameters, and which would make the neural network larger, and it would actually increase the variance in the bad side, which is what we do, right? We can add the filter sizes, number of filters arbitrarily, so that we can capture more and more information from this image, right? So this is how it actually happens. Last week we have discussed how it is applied in a single matrix, single input matrix for single filter. What happens when we have two filters, right? First filter will be applied with one. So first filter will have set of weights and a bias. Second filter will be having a set of weights and a certain bias, which is different, and both of them will be applied with the same image matrices, right? So these RGB matrices are the same, right? So those two are same. So this is, but when you apply this, do the convolution with this weight matrix, with weight filter, and then add that with this bias, then we get a linear combination, right? Of these weights and bias with the input text for the image, and then we apply the activation function, which is the ReLU activation function, right? Then only we get the resultant for the target image. Similarly, when you have two filters, you can get another output image by doing the same operation, right? Because this is new, just look at it and try to remember what we are doing here, right? So the ReLU is activation, right? We have learned it. So this is something like X. This is like W, right? This is B, right? x times w, x will have multiply with the w, and then we add the b, right? So this is what we do in this convolutional layer. So we do it for all the filters, for this filter and this filter, and we get two output matrices, right? So just remember what we have done, because we need this idea to continue. For example, say now we have three color channels, one red, green, and blue, and we have three uh, depth for the filter as well, 1, 2, and 3. Right? So we apply each of the layers in each of the layer. First, one with the one, two, two layer, matrix with the two with the green color image, three with the blue color image, and so on. Then we add all of them, and we add the bias. We apply the value activation. Then we get the output matrix, right? When you have more and more number of filters, you can get more and more output matrices. You can make the convolutional layer arbitrarily larger by simply changing the filter size, right? If you want to capture more information, you can increase the number of filters so that it can capture more information. If we want to uh, get the information in a very narrow range, you can use a filter with a small size, like 3 by 3, right? So in this case, it is 3 by 3, right? So this height and width are equal. It is 3 by 3. Actually, we can use 1 by 1 as well, right? So we will, in future, we will explain why, what we can do with 1 by 1 filters, right? So, this is a this is also a smaller one, 3 by 3. So we can increase it for a number like a 5 by 5 and so on if you want to capture a larger grade information from the image, right? This is also a hyperparameter that you can tune in a convolutional neural network, right? Not only the number of filters and so on, and the number of layers and so on, but also the filter size, regularization, all those things are hyperparameters that you can change. The activation is generally ReLU, because these convolutional neural networks are much deeper neural networks, so you must use ReLU or similar activation function, not sigmoid or tanh, right? Okay, now let's move into the notation summary that you have to remember, right? This is not something new actually. So these are the stuff that we have discussed in the last week as well. For example, so we said that in the convolutional neural network, there are not only convolutional layers, but excuse me, there are other layers like max pooling layer and fully connected layers as well. Right? So in this case, what we are discussing about is a convolutional layer. Suppose our convolutional layer has the is denoted by L, right? So L is then used for indicating the layer number. So for the convolutional layer L, the filter size used is can be represented by FL, this one. And the padding for the convolutional layer can be denoted by PL, stride as SL, and NCL as the number of filters. So up to now, we have discussed about the input images that are having square input images, like if this is A, the width, the length is also A. But in this case, we are discussing about images that has height h and width w, right? Which are rectangle images. So when we have h times w input dimension for the image, or the not only the image, if it is something, if this is a convolutional layer at the middle, so it is a matrix. This is the input matrix, right? H times w, h by w. So then the output dimensions can be represented like this. See whether you can understand. Uh, L minus 1 is the earlier layer's length. This is the height of the matrix input layer from the last layer, and this is the width of the last layer, and this is the number of filters in the last layer. So these are the input dimensions to the current convolutional layer. So because they are coming from the earlier layer, which is L minus 1, we are using the notation L minus 1 for all the L's, right? So the current layer is L, right? So we are referring to the input dimensions are relevant to the earlier layers, height, width, and number of filters. So when you multiply all those things, you get the volume of values. Or these are the dimensions of the tensor, right? This times this. So once you have processed in this convolution layer, what we get as the output is as this: NHL, NWL, and NCL. So L is the current layer number, right? So the dimensions of the NHL and NWL are as follows. If you can remember what we have learned in the last week, so this is the notation. This is how we calculate the height of this matrix, and this is the width of the matrix. Right. So we are here. I mentioned these are the flow operation. Flow means if it is something like 3.7, the flow of 3.7 is 3. Right? So this is how we calculate. So N P means the padding, right? Plus 2P PL minus FL, the filter size, divided by the stride plus 1. So the other width also the same thing. So in here, well, NW, L minus W, W is used. For NH, L minus 1, H is used. Right? These are the output dimensions. These are the filter dimensions. So you can remember, right? So filter is a square in general, right? So that is why uh, both height and width are FL and FL, and the number of channels are L minus 1 C. Right. These are the activation dimensions. That means for all of the inputs, for all of the channels, we should have the activations. Means after we apply the linear combination, we should apply the ReLU activation. Then this is the value that we get, right? So once you multiply this filter dimension, this is the filter dimension. times the channels, number of channels, then you get the weight dimension. That means when there are several filters, for each of the filter, these are the dimensions. When there are many filters, should be multiplied by the number of channels. For each of the values, we should have weight values. Right? For each of the channels, we should have a bias as well. So when you are defining the tensor, all the other values should be one by NC. That is why I just added 1 to make you understand when we are defining this in TensorFlow or NumPy. This is how you should define the tensor, because NCL is just a number. But when you are adding, for example, when you multiply this weight tensor with the x value, and then you add, or the previous activation, and then you add the bias, you should do a tensor like this to add the value, right? When you do the some example, you will understand how to do it. Right? So this is actually the example that we are going to do the today's lesson as the today's tutorial. Right? This is known as the LENet, LENet. I said that so LENet 5. So this is not the original version of the LENet. Right? So LE stands for Jan LeCun's LE, LeCun's LE, LENet. So Jan LeCun was one of the 3 people who got the Turing Award a couple of years ago for the deep learning, for the innovation of deep learning. Not only Jan LeCun was one of them. Jan LeCun, Yoshio Bengio, and Jeffrey Hinton. So those people were the pioneers of deep learning, right? So in 1998, he published this paper about LENet, which is about something about image classification. And so this is not the exact original version of LENet, because some of the features, some of the techniques that were used in the original paper are now obsolete. LENet 5 is the modern version, modern adapted version of LENet. So that's why we are learning it, not the older obsolete technologies that you see in the old paper. But although this is the old paper, these concepts were the basics of the modern convolutional neural networks. That is why we are learning this LENet for convolutional neural networks for the first time. Right. So this is the convolutional neural network. So now, can you remember the theory that we have learned, right? So we said that so this is the input image. And then we apply convolutional layer, pooling layer, convolutional layer, pooling layer, and 2 fully connected layers. And then we apply the softmax layer. This is all with this LENet 5, right? So this is an image classifier. This is why we have softmax classifier, right? So now these are the dimensions. These images are 32 by 32. 3 are for the 3 channels, RGB channels. So this is a 3-dimensional image tensor. And then we apply a convolution layer, which has the filter size of 5, stride of 1, and 6 filters, and c equals 6. So what happens is, when you can using the earlier, using this equation, using this quotation, you can find the dimensions of these, the resultant matrix. So here it was 32 by 32, right? The depth was 3. So now we apply 6 filters. So the depth would definitely be 6, right? So it is definitely 6. What has changed was the front dimensions. 32 by 32 was reduced to 28 by 28. Right. So I have a little bit changed the sizes and the depth little by little, but not in the scale. But you can have some understanding what happens during the progress throughout this convolutional neural network. Okay? So once we apply the convolutional layer, then we apply a pooling layer. And the pooling layer, you know, right? You don't train any weights and biases. What we have is only a filter size is 2. Generally, we say that we don't use even number filters, but here we use it. Right? But the style is also 2. So what is used is the max pooling. So we said that there are 2 types of pooling, average pooling and max pooling. But in most of the cases, in today implementations, we are using max pooling. That means we take the pool and we take the maximum value of that pool. So in average pooling, we take the average of the given pool. So this max pooling is used to get the most significant features from this tensor. Right? With max pooling, this information will get reduced in this step. Right? So the noise or the less significant information from this step will be removed when we come to this stage. That is the idea of using this max pool. Excuse me. Okay. Now, what we do is we apply with the pooling operation. The filter size remains the same, right? The 6 earlier, the number of the depth of was 6. Still the depth is 6, but in here it may seem like much deeper, right? So it's not correct. The depth is the same, but the depth is same, but the dimensions of the face is reduced from 28 to 14, right? Then we use the second convolutional layer, which is having a filter size of 5. It is a 5 by 5 filter, stride of 1. That means no skipping. And the filter size and the number of filters are 16. That means we have reduced after calculating the output, you can see the 14 by 14 is reduced to 10 by 10. Because the number of filters are 60, it was increased. The depth is increased, right? So the length is this one is higher than this one, right? The depth. And then we apply another pooling operation, which is also max pool with the filter size of 2 by 2, filter of 2 by 2, the stride of 2. And what we get is the same filter size 16. And the dimensions, the first 2 dimensions are reduced from 10 to 5, 10 to 5. And this is what we get. Okay. So if you look at what has happened during these operations, you can see in the earlier case, the front dimension, first 2 dimensions are larger. So those dimensions got reduced again and again, right? Continuously. 32 by 32 is reduced to 28 by 28, is reduced to 14 by 14, then it is reduced to 10 by 10, and then 5 by 5. What happened to the number of filters or the depth? It was increased. So earlier there are only 3 color channels. Then with the number of filters, it was increased to 6. Then it was increased to 6. It stayed the same. And then again with the convolution, it was increased to 16. With the pooling, it was not changed, it's remained at 60. So when you see some other neural networks, you will see this pattern clearly, right? First 2 dimensions or the face size is getting reduced, is getting smaller, but the depth the length of this block is increased, right? Here the depth is very short, increased, right? The actual pooling and convolution, the depth should not be changed, right? From in the pooling operation, because only the front value is getting changed, it is getting reduced, but the depth doesn't change. And what happens during the LNet 5 is come up with this dimension. Here you would find how many values are there in this case. 5 times 5 times 60. That is 400 values. Right? So these 400 values are applied to fully connected network. So we call it FC3. So because that was the notation there, I use it. Otherwise, it should be fully connected 1, right? The first layer. So here it was 3, so I have also used it. This is fully connected 3 and this is fully connected 4. Right? 1 and 2 were missing due to some reason, I don't know. So generally, so what happened is this 400 dimensions, which were the number of parameters in this tensor, was reduced to 120 with this fully connected layer. With this fully connected layer, this 120 parameters will be reduced to 84. With softmax layer, we can reduce it to, say, like 10. 10 means we can select 10 classes for the classifier. Like suppose there are 10 classes which we want to classify. With softmax classifier, we can classify the 10 classes, right? Let's start with the image. We use convolutional pooling one by one, several times, reducing the phase size, increasing the depth, and finally we apply some nearby fully connected layers, reduce the size, and come to the final stage or the output layer, which may be a softmax layer or some fixation related layer, right? This is the structure of this LENet 5 represents the typical structure or the architecture of a convolutional neural network, which can be said as the one of the earliest convolutional neural network, successful convolutional neural networks that were developed. Right? So these are the numbers of these layers, right? Input is there. So say this is the input. Then we apply the convolutional 1, filter size 5 and stride 1, filter 5, stride 1, pool 1, convolutional 2, filter 5, stride 1, pool 2, FC3, F3, 4, softmax. So these are the activation shape dimensions. These are the activation size. You can see it is also reduced. When you look at the number of parameters, right? So number of activation is reduced means the number of so the information is getting kind of focused into this 10 step by step, right? 3,000 to 4,000 bit increase, when 1,000, 100, 1,600, 400, 120, 84, 10, right? This reduce. The number of parameters, if you think about the number of parameters, the input layer, there are no parameters. Because input layer, there are no weights or biases. In the pooling layer also, you can see there are no pooling 1 layer, there are no parameters. Pooling 2 layer also, there are no parameters, because we said that we are not training any weights or biases in the pooling layer, right? We are only having numbers to be trained, weights and biases to be trained in convolutional layer and convolutional layers and the fully connected layers. In here, you can see in convolutional layers, there are only few parameters, but compared to the convolutional layers, fully connected layers have 48,000, 10,000 number of parameters, right? In convolutional layer, there are 456, in convolutional 2, 2014, 2416, But when it comes to fully connected layers, there are 48,000 and 10,000 number of parameters. That means fully connected layers, as we discussed in the last week also, when we are fully connected, we have to do the combination, check the combinations of all the parameters. So that is why the number of weights and the biases are very high, right? So that is why we can't use only the fully connected layers for this image classification, right? So which is very inefficient and is prone to overfitting when we are having high number of parameters. So, but that's what we have discussed it in the last week, right? So, but once we apply several convolutional and pooling, and because the number of parameters are reduced, now we can apply some fully connected layers in the last few layers before we get the final output. So the huge number of parameters that were there in this input layer was reduced when we are coming into the fully connected layers, right? That is something that you have to remember. We were using convolutional and pooling layers in the earlier phases, reduce the information, reduce the noise, and once we come up to when we have reduced the information to a certain level, then we apply the fully connected layers, and then we use the softmax or whatever the output layer to get the output. Still, the fully connected layers have more number of parameters than the convolutional layers, right? Just remember how effective the convolutional layers are, right? So because when it comes to convolutional layer, the only parameters that you have to train are the filter, vectors, and the bias, right? If there are many filters, you have to train all of them. Otherwise, if you are using a single filter, you will have to use only the weight values related to those filters, right? Okay, now let's look at this one. What is this? This is known as the AlexNet, another architecture. This was, if I remember, this was published in 2012 by a team led by Professor Jeffrey Hinton in an image classification competition. So they won this competition, and that was the end of AI winter that was there up to now, up to then. So then only the AI has started to boom. Like people got fascinated by the performance of this architecture with this AlexNet. So this was the architecture of that critical uh, system, right? So this AlexNet, which is also kind of similar to the LENet, because almost all the convolutional neural networks are the same, but this is much more larger, right? So it's much longer, and the sizes, the dimensions are a bit larger, right? So in the earlier case, it was 33 times 32 times 5, 3, 32, 32, 3, but in this case, it is like 227 by 3. 3 for the number of channels, RGB channels, right? So on the filter size is also different. 11, stride is 4, number of filter is 96. And like in the LENet, this convolutional layer, max pooling layer, convolutional layer, max pooling layer, convolutional layer, again a convolutional layer, again a convolutional layer, and a max pooling layer is used. And then two polyconnected layer followed by a softmax classifier. This is also a image classifier, right? And here also you can see that image font size has reduced. 227 by 227 is reduced to 55 by 55 to 27 by 27. Then it remains same, 27 by 27, and reduced to 13 by 13, remain the same, 13 by 13, right? Remain the same, 13 by 13, 13 by 13. then reduce to 6 by 6. Then what we do is we take all the values in this tensor, apply a fully connected layer. That means we combine all the combinations of these values, reduce it to, so here there we reduce it to 9,260. Then another fully connected layer, reduce it to 4,096. Another fully connected layer. Actually, this is the output of this layer is 9,460, right? So there's no fully connected layer here, right? So fully connected layer 1 is reducing this number of parameters into this number of parameters. Fully connected 2 is just keeping the same value. And then we apply the softmax layer. Is classifying the 1,000 images. Here you can see that unlike the earlier case, we are using in this convolutional tool, we are using a same convolution. That means we keep the same 27 by 27 as the output as well by using padding, right? In the last week, we have discussed how to use the padding to keep the same dimensions in the front. But because we have changed the number of filters to 256, the depth has increased from 96 to 256, right? The pooling layer, nothing happens to the depth, but the front first two dimensions was reduced. That is the idea of max pooling, right? And the same convolution is applied. Means the 13 by 13 is remain the same, but we have, because we have used 384 filters, the depth was increased. Earlier it was 256, right? Again, the same convolution is applied, right? And then same convolution is applied, is also reduced from 386 to 256. Max pooling is applied to reduce the first two dimensions, 13 by 13 to 6 by 6. So once we have reduced this huge amount of information that we have seen in the earlier parts of the neural network to this level, like 6 by 6 by 256, which may be like 9,260, then only we can apply the fully connected layers easily without many number of parameters, and we can use the softmax layer. So if we started use the fully connected layers here, they would be very large in size, right? As we discussed in the last week, we discussed an example where there would be 3 billion parameters required for a fully connected layer, right? But in this case, there are not that much parameters. 9,000, 4,000 number of parameters for the fully connected layer. The earlier layers are convolutional and pooling layers, which take care of the images, right? This is the power of AlexNet. This is not the exact AlexNet, but this is a modified version too. Because some of the techniques that were used in that time are not the optimum way to use neural network. So we have updated them. That is why this is the updated version that you can use even now for your image classification tasks. Okay, that is for the AlexNet. Now let's look at another neural network architecture, convolutional neural network architecture, which is the ResNet. It stands for the residual net, right? What is a ResNet? Why it is used? So when we want to do much higher level of intelligent operations, we said that we need much depth in a neural network, right? So deeper the neural network is, it would have better performance, right? Means better outcome, much intelligence. Right? So like we said that it's intelligence is increasing exponentially with the number of layers, right? So, but the problem is that as we discussed earlier, so when we increase the depth, the vanishing gradient problem and the exploding gradient problems get significant, and we would no longer be able to add more layers due to this problem. So we explain the things that you can do to reduce these effects, but still, when we are increasing the number of layers like hundreds and thousands, then this effect will be there, right? So there would be a limit for the depth. So this is another solution that you can use to get rid of these problems, managing and exploring radius. So with the number of layers, so what you can see is that theoretically we should be having, when we are having much intelligence, our error should be decreased, right? But in practice, when we are increasing the number of layers after a certain depth, then the error gets increased. So that is how we identify that we can no more add more depth into the neural network. So we have to use some other techniques like residual network techniques. So actual residual network is using some neural network shortcuts or bypass to the neural network. So we will discuss what they are. What are those shortcuts or the bypasses that you can use for a neural network, especially this for this convolutional neural networks, right? So this ResNet is actually a convolutional neural network that are having these shortcuts. So these neural network layers that are having these residual paths, or these shortcuts are known as residual blocks, right? Let's see what is this residual block is. So first see that, so this is relevant to, suppose this is a dense layer, right? So for the simplicity, just take it as a dense layer, right? Then we get AL as the activation as the input for this dense layer. What we get out from the dense layer is a AL minus 1. Once we have finished this layer, AL minus 1. And after this layer, what we get is the activation AL plus 1. After that, we get the AL plus 2, right? So what we are doing as a shortcut is that we are adding this AL to this layer before we apply this activation function to get the AL plus 2. So that means we do some linear combination with this AL plus 1, and then we add this AL, and then we apply the activation function. So this is another way to explain it. We get the AL, then we do this first layer, we do the linear combination, which is AL times WL plus 1 times BL plus 1. So this is the linear combination. We get the Z, right? ZL plus 1. And then we apply the activation function for the first layer. AL plus 1 is G, which is the activation function of ZL plus 1, right? So we get the linear combination ZL plus 1. Then we apply it to the activation function, which is the L function. Get the AL plus 1, which is this one, right? So we get the AL plus 1. So now in the second layer, the same thing happens. We have a linear combination where we are applying this AL plus 1 to the WL plus 2, this layers with matrix, and then we add the bias BL plus 2, and then you get the Z value ZL plus 2. And if there is no shortcut, so what happens is then we apply the activation function, and then we get the AL plus 2 and output. But what happens is the shortcut, we get this AL plus this AL value and add to this ZL plus 1. Here you can see ZL plus 1 plus AL. ZL plus 2 is this one. AL is this A, right? So we add this AL to this ZL plus 2. Then we get this value instead of this ZL plus 2. Then we apply the same activation function, and then we get the AL plus 2 activation value. this is all about this residual block. Nothing serious, right? So what happens here? This is only for a residual block. That means this is a small part of the convolutional neural network that the residual shortcut is applied. Right. So throughout the neural network, you can use this shortcut to reduce the effect of exploding gradient and vanishing gradient. So what happens is something like this. So suppose now we have added this AL like this, right? This is this AL. What is ZL plus 2? Is ZL plus 2 is this one, right? WL plus 2 plus AL plus 1 plus BL plus 2. Say now this one was something this is a deeper layer, right? So now what happens is we are applying the weight decay. Weight decay is the L2 regularization, right? If you can remember, so this is also known as the L2 regularization. I don't know whether you can remember L2 regularization. So in the weight decay, what happens is this weight will be reduced more and more, right? And with the lesser the gradient is, the vanishing gradient, this W1 and the WL plus 2 and the BL plus 2 will become smaller and smaller. So it may go to the 0. So if we said L plus 2 was there, only this one was there, what happens is if this W and L, B, if W and B are going to 0, this Z L plus 2 would be going to 0, right? So this AL plus 2 would also go to 0. But when we add this AL coming from this location, what happens is now if this ZL plus 2, which is going to 0 due to the get being 0 of this W and B, still we have this AL, right? AL is not 0. It's the same identity function as the earlier one, but still you can get the activation of this AL and go to the next layer instead of getting the value of 0 to this value, right? Because when these values are getting 0, if we are getting 0 for this value, all the other layers behind it will also get 0. So then you can't learn it, right? But because when these two are getting 0, we still have AL. We can pass the same AL to this AL plus 2, and we can do something. We can process. We can continue the neural network operations into more depth. So if this Z L plus 2 is good, if it is significant, we don't need this AL. We can proceed with AL plus 2, but if this is going to 0 or very small, then we can use this AL and assign it and get the activation function and assign to this AL plus 2 and continue the neural network. So that is how it is working if you think intuitively. Right? In the earlier case, what we have defined is about this residual blocks. Right? So this is a residual block. This is a residual block. But when it comes to a very large convolutional neural network like this, right? This is a three-layer neural network. And so this each of the layer is a convolutional layer, right? And there would be pooling layers as well, right? Actually, there's all of them are convolutional layers, right? Yeah. So because this neural network is so deep, too large, too long means too deep, right? Then you can apply this shortcuts like this one, right? Bypassing each of the layers, right? This layer is bypassed by adding this path. Similarly, we can add bypass shortcuts for each of these for each of the for two of the layers, right? So this is how we implement this RESTnet for a very deep and convolutional neural network. Excuse me. I think now you get it, right? With this way, you can avoid the problem of vanishing gradient and exploding gradient affecting the neural network from start having higher errors, training errors, right? Okay, that is about ResNet. Now we are moving to another type of uh, convolutional neural network architecture known as inception network. Now the problem is like this. Okay? We said that as hyperparameters, you can change the dimensions of the filter, right? Excuse me. I said that generally we are using 3x3 filters. But you can change it to like 1x1 or 5x5 and so on. And sometimes then we after several convolutional layers or one after the other, we apply the pooling layer, X pooling layers. So how do you know that which filter should be applied now and which one at the second phase? We don't know, right? We don't know whether you should apply 3x3 and then max pool or 5x5 and again 5x5. We don't know, right? We are just doing a trial and error and we find this one is working good, so we are using this. But that is not the, but we don't know exactly the hyperparameters that we should apply. So in inception net, what they do is they are applying all the filters. Say you get the input tensor like this. We apply 1x1 filter and get the green color part of the tensor, output filter, output tensor. And we apply the get the same tensor and apply the 3x3 filter and get this blue color tensor part. And then we apply a 5x5 filter, the same input and get this purple color tensor. And also you apply the max pool for this tensor and then we get the yellow color tensor. So we concatenate all these tensors together as the output tensor. This is the idea of inception. Right? So this is like a like alchemy, right? So you try all those things, check whether whatever comes good, we are trying to get it, right? Excuse me. I'm not well today, sorry. So will be finished after several minutes. Sorry for the inconvenience. Okay. Mhm. So now the problem is that when we are calculating these values, like this 3 by 3 and 5 by 5 filters, those operations are highly expensive, computationally expensive. Although those are possible, so just applying those operations, these convolutions are highly computationally expensive. So it is not that easy to do it, right? So now what we have done is, instead of directly applying these filters, for the one by filters, we can simply apply. For the max pooling, we can simply apply, and then we use a 1 by 1 convolution to match the dimensions of the output tensor. For the second one, the 3 by 3 and the 5 by 5 tensors, first we apply a 1 by 1 convolution, like this one, and then we apply a 3 by 3 convolution. For this 5 by 5 convolution also, first we apply a 1 by 1 convolution, and then only we apply a 5 by 5 convolution. So in this layer, it is actually reducing the amount of information which is known as bottleneck, right? So although it is reducing the information, but still it is working fine sufficiently enough. And then you can apply the smaller amount of computation with these combination of these two layers, instead of using just trying to match this dimension to this dimension directly. We can add the intermediate 1 by 1 convolution for this 3 by 3 and 5 by 5 networks. That is also a technique that is used in inception neural network. So then when we get the input sensor or the previous activation on the previous layer, we apply first to the first 1 by 1 convolution, and one is applied the 1 by 1 convolution, and then apply the 3 by 3 convolution, and another 1 by 1 convolution followed by a 5 by 5 convolution, max pool, and 1 by 1 convolution to match the dimensions, and then we concatenate all of them together. Then we get this output tensor, which is this one. This is the inception neural network. This is actually a block of a inception neural network. So if you look at the complete inception neural network, so this is also actually part of the inception network, because inception network has like hundreds and sometimes thousands of layers, because it can handle that much of depth, right? So if you look at each of them, right, those are like you can see how each of the block there are these blocks that are relevant to our inception block, right? For some of the layers, we can see there are some max pooling layers are applied to change the dimensions or reduce the dimensions, right? And also you can see there are some output blocks are there in the middle. So this is the input side. This is the way the signal is passing. But before it is passing at this end, you check some special neural network with the softmax classifier, and then we get the output. Here also we do the same. So the idea is it add some check or some make sure the features are working correctly at these levels, and also it adds some effect of regularization into the neural network because these networks are so deep. So time to time we do these checks, we do these outputs to make sure it is working correct. That is another technique that is used in inception neural network. So actually, how if you have thought why this name inception has come, actually they have used the name from this movie. Right, so it says it's a very famous movie, right? So like going deeper into the dreams. So actually they were having this meme, like we have to go deep. In order to go deep, they were using this inception neural network. That is actually meme, but which they have actually uh, added in their publication paper. Yes. So that is kind of funny, right? Okay, this is what I have explained, right? That is all for today's lesson. If you have any questions, you can ask.